Welcome to my classroom. In this video, I will talk about the inequality AM is greater than GM, that is, the arithmetic mean is greater than or equals to geometric mean, and prove it by backward induction. The discussion will involve the idea of mathematical induction. So this video is for senior form students who want to learn more about the inequality and MI. Let us start with the simple version of the inequality. Here, A and B are non-negative numbers. The arithmetic mean A plus B over 2 is greater than or equals to the geometric mean square root of A times B. The second part of the statement is the equality holds if and only if A equals B. There are two directions to consider. For this simple version, you may pause the video and work on your own first. For A, B non-negative numbers, we can rewrite A as square root of root A. Similarly, for B, arrange the terms so that it gives a perfect square, which is non-negative. Rearrange the terms and we got the AM, which is greater than or equals to GM. The first part is done. For the second part, when two terms equal, A equals B, by direct substitution, we see the equality holds obviously. On the other side, when the equality holds, that is A plus B over 2 equals to square root of AB, by the previous result, we have the perfect square equals 0. In other words, A equals B. Therefore, the second part is done, and so is the whole statement. Here is the general statement. For n non-negative terms, denoted by x1, x2 up to xn, the arithmetic mean, the sum of the term divided by n, is greater than or equals to the nth root of the product of the terms. The second part of the statement is the equality holds if and only if all the terms are equal. As the statements involve the natural numbers n, we can think of mathematical induction to prove it. Yet, it is hard to derive the statement from n equals k to n equals to k plus 1. We need to do it with a special version of MI. It is the backward induction. Let us recall the standard version of MI first. There are two main steps in the argument. The first step is the initial step, that is to prove the statement is true for n equals 1, that is P1 is true. The second step is the induction step, that is assume the statement is true for n equals k and prove the statement is also true for n equals to k plus 1. Then, by the principle of mathematical induction, we get P of n is true for all positive integers n. Let me make use of a diagram to illustrate the mechanism. Here, the first statement is proved to be true. This is the induction step. Whenever P of k is true, P of k plus 1 is also true. Now, if you want to check a statement where n equals m, suppose m is here. We start from P1. By induction step, we have P2. By the induction step again, we have P3. Similarly, we have Pm, the statement we want to check. As m is an arbitrary positive integer, so we can see that the statement is true for all positive integers, n. Now, the backward induction, it involves two steps as well. The initial step is to prove infinitely many statements. Of course, it doesn't mean to prove all statements. For example, to prove the statements of n equals to 2 to the power r, where r is any positive integers. So, The initial steps includes infinitely many statements, but not all. The induction step is to induce backwardly. That is, assume the statement is true for n equals k. Then, to prove the statement is also true for n equals to k minus 1. Then, by the principle of backward induction, the statement is true for all positive integers n. Again, I used a diagram to illustrate the ideas. The initial steps involve infinitely many statements. The induction step induces backwardly. Suppose we want to check P of M, and M is here. Since there are infinitely many true statements proved by the initial step, there is a true statement P of L such that M is smaller than L. Apply the induction step, we work backwardly to prove P of M is also true. As M is arbitrary, therefore P of n is true for all positive integers n. Think about the logic of the argument carefully and make sure you understand the structure of the argument before you go on with the video. We are going to prove the general statement by backward induction. As mentioned earlier, there are two main steps. The initial step is to prove the statement is true for infinitely many choices of n. Because of the structure of the inequality, we are going to prove the statement is true for n equals to 2 to the power r, where r is any positive integer. So there are infinitely many choices of n, but not all n. The induction step is done by backward induction. Now, to prove the first step, that is to prove P of 2 to the power r is true for all positive integers r. We use the simple version of mi to do this. Again, there are two steps. The initial step. For r equals 1, that is the statement when n equals 2, P of 2 has been proved by simple version in the previous slide. So the initial step is done. The next step is the induction step. Assume P of 2 to the power k is true for some positive integers k. Consider P of 2 to the power k plus 1. We start with the left-hand side of the inequality, that is the am of 2 to the power k plus 1 terms. Split the terms into two groups. The first group contains 2 to the power k terms, and so as the second group. By the assumption P of 2 to the power k, am is greater than or equal to gm, we have the gm of two groups of 2 to the power k terms. Now, we have am of two big terms. By P of 2, we have the gm of 2 to the power k plus 1 terms. The first part is done. Now, the second part, about the equality. If all the terms are equal, by simple substitution, the equality obviously holds. So, consider the other side. That is, when two means are equal. We would like to derive all the terms equal. For the left-hand side, we split the terms into two groups, like before, and on the right-hand side, we also split the terms into two groups. According to the assumption P of 2 to the power k, this product is less than or equals to the product of the am. On the other hand, the sum of two terms, according to P of 2, we have this greater than or equals to the gm. And since these two expressions are equal, it forced the inequality side change to the equality. In other words, we have this equality. According to the structure, we can apply P of 2 so that these two expressions are equal. In other words, the sum of the first two k terms is equal to the sum of the last two k terms. Rearrange the terms and apply the same argument. We have the equation 2. Combine the two equations 1 and 2. We cancel the common terms and we have x1 equals to x sub 2 to the power k plus 1. So we have two terms equal. Apply the argument similarly. We have all terms equal. And therefore, the second part is done. Combine these two parts. By the principle of mathematical inductions, we have the statement p of 2 to the power r is true for all positive integers r. So far, we have proved the statement is true for infinitely many choices of n. That is the initial part of the backward induction. Now, we go to the induction step. That is, we assume p of k is true, and to prove p of k minus 1 is also true. For the first part, given any non-negative numbers x1, x2 up to x sub k minus 1. In order to use the assumption p of k, we construct a new term, that is xk, which is the am of the given k minus 1 terms. Now, by the assumption p of k, we have the k terms am greater than or equal to the gm. Substitute xk to the left-hand side of the inequality. We have the left-hand side is in fact equals to xk. And take the power so that we can cancel xk. And then take the k minus 1 root. So for the given k minus 1 terms, we have am is greater than or equals to the gm. The first part is done. Now the second part, the equality. If all terms equals, by direct substitution, the equality holds. So consider the converse. Suppose the am of the given k minus 1 terms equals to the gm. Like before, we define a new term, xk, which is the gm of the given k minus 1 terms, and therefore it is also the am. First, we move the surd by taking the power. Multiply xk to both sides, so that the right-hand side is a product of k terms. By the assumption of p of k, it is less than or equal to the am with the power k. Replace the sum of k minus 1 terms by xk, simplify, and we have xk to the power k. It equals to the left-hand side, and thus the inequality sign is forced to be the equal sign. We have the am of k terms equal to the gm. By the assumption p of k, all terms equal, in particular, the first k minus 1 terms. So the second part is done. By the principle of backward induction, the general statement is proved. The inequality am is greater than gm, both the simple version and the general statement is quite a good tool for finding the extreme values or proving other statements. Although the proof of the inequality is a bit complicated, it demonstrates the idea of backward induction and some useful techniques. I suppose it is worth to go through the proof to understand and appreciate the ideas behind. It is a good exercise to prove the statement of 3 terms without mi. You will use the techniques demonstrated in the proof. Learning by doing. If you are able to complete the proof of 3 terms, it means that you have a good understanding of the proof of the general statement by backward induction. Try it.